Hi everyone. This is the paper Measuring Violations of Positive Involvement in Voting. My name's Eric Pacuit, and this is joint work with Wes Holliday. Let's start with a question. What's the chance that voting for your favorite candidate causes that candidate to lose using your favorite voting method? Intuitively, of course, we would like the answer to that to be none at all. There should be no chance that voting for your favorite candidate increases the chances that that candidate will actually lose the election. The key idea here is that unequivocal increase in support for a candidate should never result in that candidate going from being a winner to being a loser. And there's two ways to sort of formalize this intuitive idea. The first is the axiom we're going to talk about in this paper, positive involvement. Positive involvement says if a candidate X is a winner given a preference profile P, a preference profile is just sort of, you can think of it as an election scenario. So given an election, candidate X is a winner, and P star is obtained from P by adding just one new voter who ranks X in first place. So one voter comes in and they rank X in first place. Then, according to positive involvement, X should still be a winner in P star. A related axiom is monotonicity. Monotonicity says if a candidate X is a winner given a preference profile P, and P prime is obtained from P by one voter moving X up in their ranking. So one voter had Y above X, and then they decided to lift X just above Y. Then X should still be a winner in P prime. Now, monotonicity is a fixed electorate axiom because the set of voters and candidates remains fixed. And positive involvement is a variable electorate axiom because the set of voters is changing between the two profiles. In this talk, we're going to focus on positive involvement. Surprisingly, many voting methods actually violate positive involvement. Here's a list of the voting methods that violate positive involvement. You can see the definition of these methods in our paper, and including some examples to illustrate the violations of positive involvement. The voting methods that satisfy positive involvement include all positional scoring rules, for example, Borda and plurality. Instant runoff satisfies positive involvement. This is currently being used to elect the mayor in New York City. A recently proposed voting method, split cycle, something that Wes and I have been working on, actually satisfies positive involvement. Now, before getting to our quantitative analysis, let me just say a little bit about the history of positive involvement. This is related to a paradox of voting known as the no-show paradox, which was introduced by Steve Brams and Peter Fishburne. But what they were interested in, the property they were interested in, is what is now called negative involvement. Negative involvement says adding a new voter who ranks a candidate last should not result in that candidate going from being a loser to being a winner. Then later on, Moulin changed the meaning of the no-show paradox to refer to violations of a different property known as participation. And participation really applies to resolute voting methods. These are voting methods that always elect a single winner. In our paper, we're interested in irresolute voting methods that might elect more than one candidate as a winner. And then you use like a tie-breaking or something to determine who the ultimate winner might be. So a resolute voting method satisfies participation if adding a new voter who ranks X above Y cannot result in a change from X being the unique winner to Y being the unique winner. But if you think about it, participation is a very different type of axiom than both positive involvement and negative involvement, because Moulin is considering this voter that does have X ranked above Y, but this voter might have many other candidates ranked above X and Y, and many candidates ranked below X and Y. Finally, Perez has a very nice paper where he studies what he calls the strong no-show paradox, which is essentially just positive involvement. And he concludes that positive involvement is a common flaw of many Condorcet-consistent voting methods. Now, these are voting methods that always elect a Condorcet winner. This is a candidate that beats every other candidate in a head-to-head matchup. Now, interestingly, the Condorcet-consistent voting method split cycle, this is what Wes and I have been working on. So this is a Condorcet-consistent voting method that actually satisfies positive involvement. In the interest of time, we're just going to present two examples of voting methods that violate positive involvement. Many more examples can be found in our paper. The first method we're going to talk about is Buckland. So Buckland works as follows. Given a profile P and a candidate A, and some positive integer n, say that A is an nth level majority winner if a strict majority of voters rank A in nth place or higher. So a second level majority winner is a candidate for which there's a strict majority of voters that rank that candidate either in position 1 or position 2, level 1 or level 2. And let k now be the smallest positive integer for which there is at least one kth level majority winner. Now, Buckland is going to select the kth level majority winners for whom the most voters rank them in kth place or higher. So here's an example of two profiles that witness the fact that Buckland violates positive involvement. We represent profiles as anonymous profiles, so the first row here represents the number of voters that submit each ranking to the selection. We are assuming that voters submit linear orders, so this column right here means that one voter submitted the ranking A above B above C above E above D. Now, in this profile right here, the Buckland winner is C. There are no first level majority winners, there are no second level majority winners, but there are third level majority winners. Candidate C has everybody ranks them either first, second, or third. There's also candidate A is a third level majority winner. But more people rank candidate C in position 1, 2, or 3 than candidate A in position 1, 2, or 3. So that's why C is the unique Buckland winner. Now, a new voter enters the election, this voter right over here. This voter ranks candidate C, the winner of the previous election, in first place. Now, with the addition of this new voter, now there is, in fact, a second level majority winner. Candidate E has 3 voters rank candidate E in either position 1 or position 2. And that means that E, since E is the only candidate with that property, candidate E is the unique Buckland winner. So the addition of this one voter that ranks C in first place makes C go from a winner to a loser. So this is an example of a profile of two profiles that witness the fact that Buckland violates positive involvement. The next voting method we're going to talk about is beat path. But before I define beat path, we first need a little bit of terminology. So given a profile P, we're going to write X of P for the set of candidates in P. We're going to write V of P for the set of voters in P. And for a voter I, we'll write P sub I for I's ranking in P. So if you write A P sub I B, that means voter I ranks A strictly above candidate B. And don't forget that we're assuming that the voters submit linear orderings over the candidates. Now, the margin for a candidate A over a candidate B is defined as follows. The margin of A over B is the number of voters that rank A above B in the profile P minus the number of voters that rank B above A in the profile P. So that's what the margin of A over B is. Now, if the margin of A over B is positive, then we say that A is majority preferred to B. If it's negative, then we say that B is majority preferred to A, because a positive margin means there's a strict majority of voters that rank A above B. The margin, of course, could be 0, in which case you have the same number of voters rank A above B as B above A. So there's a tie between A and B. Now, beat path works as follows. Let's say that a path from candidate A to candidate B is a sequence of candidates, x1 to xn. They're all distinct candidates, such that A is the first element of the sequence, B is the last element of the sequence, and for each k, xk is majority preferred to xk plus 1. So every candidate in that sequence is majority preferred to the next candidate. The strength of a path is just the minimum margin along that path. Now, we say that A defeats B in P according to beat path if the strength of the strongest path from A to B is strictly greater than the strength of the strongest path from B to A. And then the beat path winners are the set of undefeated candidates. So let's look at an example. Here are two profiles. The first thing I want to note is that we can represent a profile in terms of a margin graph. So this is a graph where the nodes are the candidates, there's an arrow from A to B means that A is majority preferred to B. It's going to be labeled with the margin of victory. So this arrow right here means that the margin of A over B is 1. Now, in this profile right here, the beat path winners is everybody. A, B, C, and D are all of the beat path winners. Now, why is that? Well, let's just look at an example. Does A defeat D according to beat path? Well, A is majority preferred to D. The margin of victory of A over D is 1. So there's a direct path from A to D, and the weight of that path is 1. There's another path from A to D. A beats B, and B beats D. The strength of that path is also 1, because you look at the minimum margin along that path. So, in fact, every path from A to D has strength 1. What about from D to A? Well, there is also a path back from D to A. D beats C, and C beats A. The strength of that path is 1. So if you were to just check what are all the paths back from D to A and all the paths from A to D, you'll see that the strength of those paths are all 1. So that means A does not defeat D, because the strength of the strongest path from A to D is not strictly greater than the strength of the strongest path from D to A. So, and that's true for all of the candidates. So all the candidates are tied according to beat path. Now, a new voter comes in. This new voter enters the election. This voter has B ranked in first place. This will, of course, change the margin graph in the following way. The arrow from A to B goes away because this voter ranks B above A, and here the margin of victory of A over B is 1, so now there's a tie between B and A. And then, the margin from A over D goes to 2 because this voter ranks A over D. Now, in this margin graph, it's not too hard to see that A is the unique beat path winner. You can see that primarily because there are no in arrows coming to A, so there's going to be no path back that leads back to A, and A can reach every other candidate. So A beats D directly, A beats C according to beat path because A beats D and D beats C, and then finally there's a path from A to D to C all the way back to B. So this is an example of two profiles that witness the fact that beat path violates positive involvement. In this paper, we're interested in a quantitative analysis of positive involvement. So let's say that a profile P witnesses a violation of PI for some voting method F if there exists a voter I in P such that I's favorite candidate, that is the candidate that I ranks in first place, wins in the profile P minus I according to F, where P minus I is just the profile P where you remove voter I, but their I's favorite candidate does not win in the original profile P. So you have a voter I, their favorite candidate wins when I is not in the election, but loses when I is in the election. So that's what it means to witness a violation of PI. Now, the naive approach is to just simply estimate the probability that some random profile generated according to some probability model witnesses a violation of PI for some voting method F. So the idea would be to generate a bunch of profiles using some probability model, and then just figure out what are the frequency of PI violations according to different voting methods. The problem with this is that for medium to large size electorates, we should expect that this probability will be extremely low. And this is just for the mundane reason that the addition of any single voter will rarely cause someone to lose. Our main objective in this paper is to look at different ways of measuring PI violations that takes into account this basic problem. So here's the first idea, to condition on voting method disagreement. Now, suppose that voting method F violates positive involvement. And as we said, the frequency of violations for this voting method F might be quite low. However, it might be significantly higher when we condition on F picking different winners than some other voting method G that satisfies positive involvement. So what we want to do is we want to pick some voting method that satisfies positive involvement, split cycle, Borda, instant runoff, and we want to consider this conditional probability. The probability that P witnesses a PI violation for F conditional on or condition on the fact that F and G give different answers on the profile P. So here's some simulations to illustrate what happens with this conditional probability. The x-axis here in these graphs represents the number of voters in the profile. This pair, 500, 501, means that we generated 25,000 profiles with 500 voters and 5 candidates, and 25,000 profiles with 501 voters and 5 candidates, using the impartial culture model. The y-axis here is the conditional probability. The first column here is the unconditional frequency. So this is just the frequency of PI violations. And you can see that when we condition on disagreement with 3 voting methods that satisfy positive involvement, we generally get slightly higher probabilities. So the frequencies are slightly higher. It's a little bit more dramatic with split cycle, especially for uncovered set. When uncovered set differs with split cycle, it does so slightly, quite often or relatively often, because it's violating positive involvement. Now, one problem we still have is that as the number of voters increases, these conditional probabilities are still going down. And of course that makes sense, because as you get more and more voters, a single voter just won't have that much influence over the outcome of an election. This leads us to our second basic idea, that is to relativize to voter potency. So the idea here is to consider a ratio of probabilities. The numerator is going to be the probability of a PI violation. That is, the probability that there's this voter whose favorite candidate wins when they're not in the election, but doesn't win when they are in the election. But we want to compare that to the probability that that voter just causes somebody to lose. That is, when the voter is in the election, somebody wins, but when the voter is not in the election, so that candidate doesn't actually win. Now, when we relativize to voter potency, we get a better measure of violations of positive involvement. We're able to distinguish between these voting methods in a little bit nicer way, and it's not as sensitive. All the numbers don't go down to 0 when you get lots and lots of voters in the election. This leads us to the last basic idea, that of coalitional Pi. So let's say that a pair P, PC, where P is a profile and PC is a coalitional profile, that is a profile where every voter has exactly the same ranking. Every voter in C has exactly the same ranking. That pair witnesses a violation of PI just in case the unanimously top-ranked candidate in PC is a winner in P, but not in the profile P plus PC. Now, one thing to note is that the pair P, PC, the probability that that pair witnesses a violation of PI might be significantly lower than the probability that a profile witnesses a violation of PI. And that's just simply because P, PC may not witness a violation of PI, but the profile P plus PC does witness a violation of PI because you need to remove maybe a different set of voters, some voters other than C. Then we can consider relativizing to coalitional potency. So the idea is to consider this ratio right here, where the numerator is the probability that a coalition C causes A to lose, conditional on the fact that A is their favorite candidate, and the denominator is just the probability that C causes A to lose. Now, there's good justification for considering this ratio. Ratios of the form, the probability of A given B divided by the probability of A, are commonly used in confirmation theory to measure the degree of support that evidence provides a hypothesis. Thus, what we are really asking is the following. Suppose that you learn that the voters in C rank A first. To what extent does this support the hypothesis that the voters in C will cause candidate A to actually lose? And this gives us, again, another interesting measure to consider how bad certain voting methods are at violating positive involvement. Now, one last comment I want to make is about the probability models we use to generate our profiles. the graphs I've shown in this talk have all been generated using the impartial culture. And of course, one might be worried what happens when you consider other probability models. We do consider other probability models in the paper, the impartial anonymous culture, the EARN model, and so on. And we found that our measures are not incredibly sensitive to the probability model. Of course, some probability models will lead to 0 violations of positive involvement. For example, single peaked preferences will lead to 0 violations of PI. Okay, so let's conclude. So the first concluding remark is just that we think that this methodology, that of conditioning on voting method disagreement and relativizing to the influence that a voter or a coalition of voters has on the outcome, should be applied to other axioms in voting theory, for example, monotonicity or some other axioms like that. The second remark is that under certain voting methods that violate positive involvement, much of a voter's potency is turned against them, in particular against their desire to see their favorite candidate elected. Now, the probabilities might be large enough to raise real concerns in maybe small-scale elections, for example, in committees or clubs, unless you know somehow in advance that the probability models that we consider in the paper aren't relevant to the profiles generated in that club. However, for large elections, defenders of a voting method that actually violates positive involvement might simply respond, look, don't worry about it. Your vote probably won't cause your favorite candidate to lose because it probably won't influence the election at all. But this response raises what is perhaps the more serious concern about voting in large elections. Why do voters vote in large elections? And the significance of single voter axioms for large elections may in fact turn on the answer to this more general question. So thanks for listening. I hope to see you all soon. If you want to play around with the code, you can look at our GitHub account. And this has all the code to generate the graphs there to do our simulations. Thanks, and hope to see you all soon.